Welcome. Today we're diving into the fascinating world of cache memory. If you've ever wondered why some computers seem to run faster than others, cache memory is a big part of the answer. It's a small high-speed storage area that sits between the main memory and the processor, helping your computer access data much more quickly. In this video, we'll explore what cache memory is, how it works, and why it's so important for modern computing. Let's start by understanding the basics and setting the stage for a deeper look into this essential component. Cache memory is a special type of memory that stores frequently used data and instructions. Unlike your main RAM, cache is much faster but also much smaller. Its main job is to keep the processor supplied with the data it needs without delay. When the processor needs information, it first checks the cache. If the data is there, it's called a cache hit and the processor can keep working at top speed. If not, it's a cache miss and the processor has to fetch the data from slower main memory. This simple mechanism makes a huge difference in overall system performance. You might wonder, why do we need cache memory at all? The answer lies in the speed difference between the processor and main memory. Modern processors work incredibly fast, but main memory can't always keep up. This mismatch creates a bottleneck, slowing down the entire system. Cache memory bridges this gap by providing a much faster place to store and retrieve data that the processor uses most often. By doing so, it allows the processor to work more efficiently and keeps your computer running smoothly, even when handling complex tasks. Let's look at how cache memory actually works. When your processor needs data, it first checks the cache. If the data is present, it's delivered instantly. If not, the processor fetches it from main memory and stores a copy in the cache for next time. This process is managed by sophisticated algorithms that predict which data will be needed soon. The goal is to maximize the number of cache hits and minimize cache misses, ensuring the processor spends less time waiting and more time computing. Cache memory isn't just a single block. It's organized into different levels, typically called L1, L2, and L3. L1 cache is the smallest and fastest, located closest to the processor core. L2 is larger but a bit slower, and L3 is even bigger and shared among multiple cores. Each level plays a unique role in balancing speed and capacity, helping the processor access data as quickly as possible while still having enough space to store what it needs. L1 cache is the first level of cache memory and sits right inside the processor core. It's extremely fast but also very small, usually just a few kilobytes. Because it's so close to the processor, accessing data from L1 cache is almost instantaneous. This makes it perfect for storing the most frequently used instructions and data, ensuring the processor can work at maximum speed without unnecessary delays. Moving to the next level, L2 cache is larger than L1 but a bit slower. It's often located on the processor chip but not inside the core itself. L2 cache acts as a backup for L1, storing data that might not be needed as frequently but is still important for performance. By having this extra layer, the processor can still access data quickly, even if it's not in the L1 cache. L3 cache is the largest and slowest among the three main cache levels, but it still operates much faster than main memory. It's usually shared between multiple processor cores, making it essential for multi-core performance. L3 cache helps coordinate data access across cores, reducing delays and improving the efficiency of complex, multi-threaded tasks. It's important to understand the difference between cache memory and RAM. While both are types of memory, cache is much faster and smaller. RAM stores all the data and programs currently in use, while cache holds only the most critical pieces that the processor needs right away. This division of labor helps your computer run efficiently, with cache handling speed and RAM handling capacity. Whenever the processor looks for data in the cache, there are two possible outcomes: a hit or a miss. A cache hit means the data is found in the cache, allowing for instant access. A cache miss means the data isn't there, so the processor must fetch it from slower memory. The goal of cache design is to maximize hits and minimize misses, keeping the processor running at peak efficiency. There are different types of cache memory, each serving a specific purpose. Instruction cache stores program instructions, while data cache holds the actual data being processed. Some systems even have separate caches for different types of data, further optimizing performance. Understanding these types helps explain how cache memory can be so effective in speeding up your computer. Instruction cache is dedicated to storing the instructions that the processor needs to execute programs. By keeping these instructions close at hand, the processor can fetch and execute them much more quickly. This is especially important for programs that run loops or repeat certain operations, as the same instructions are needed over and over again. Data cache, on the other hand, holds the actual data being processed by the CPU. This could be anything from numbers in a calculation to the contents of a document you're editing. By keeping this data close to the processor, the system can avoid slowdowns and keep everything running smoothly, even during complex operations. Some modern processors use a unified cache which stores both instructions and data in the same space. This flexible approach allows the processor to allocate cache resources dynamically, depending on what's needed most at any given time. Unified caches can improve efficiency, especially in systems where workloads vary widely. Where cache memory is placed in a computer system matters a lot. L1 cache is inside the processor core, L2 is nearby, and L3 is shared among cores. This strategic placement ensures that the most critical data is always as close as possible to where it's needed, minimizing delays and maximizing performance. Size of the cache memory has a direct impact on computer speed. Larger caches can store more data, reducing the number of times the processor has to access slower main memory. However, bigger isn't always better. There are trade-offs in terms of cost and complexity. designers must balance size, speed, and efficiency to get the best results. Associativity refers to how cache memory is organized and how data is mapped from main memory to cache. There are different types like direct mapped, set-associative, and fully associative caches. Each type has its own strengths and weaknesses, affecting how efficiently the cache can store and retrieve data. A direct mapped cache is the simplest form of cache organization. Each block of main memory maps to exactly one location in the cache. This makes it easy to implement and fast to access, but it can lead to more cache misses if multiple blocks compete for the same spot. Set-associative cache is a compromise between direct mapped and fully associative caches. Each block of memory can go into any one of several locations, reducing the chance of cache misses. This approach is common in modern processors, offering a good balance between speed and flexibility. In a fully associative cache, any block of memory can be stored in any cache location. This maximizes flexibility and minimizes cache misses, but it's more complex and expensive to implement. Fully associative caches are usually reserved for small, specialized applications where performance is critical. When the cache is full, the system needs to decide which data to remove to make room for new information. This is where replacement policies come in. Common policies include least recently used, LRU, first in first out FIFO, and random replacement. Each has its own way of choosing which data to evict, impacting overall performance. The least recently used policy removes the data that hasn't been accessed for the longest time. This approach assumes that if data hasn't been used recently, it's less likely to be needed soon. LRU is popular because it often matches real-world usage patterns, keeping the most relevant data in the cache. First in first out is a straightforward policy that removes the oldest data in the cache, regardless of how often it's used. While simple to implement, FIFO doesn't always provide the best performance since it might evict data that's still needed by the processor. The random replacement policy selects a random cache block to replace when new data needs to be loaded. While this method is easy to implement, it can lead to unpredictable performance. It's rarely used in practice but can be useful in certain specialized systems. Write policies determine how changes to data in the cache are handled. The two main types are write-through and write-back. Write-through updates both the cache and main memory simultaneously, while write-back only updates main memory when data is removed from the cache. Each approach has its own pros and cons. With the write-through policy, every time data is written to the cache, it's also written to main memory. This ensures data consistency but can slow down performance since every write operation takes longer. Write-through is often used in systems where data integrity is more important than speed. The write-back policy only updates main memory when data is removed from the cache. This can speed up performance since fewer write operations are needed. However, it also means there's a risk of data loss if the system crashes before the cache is written back to memory. In systems with multiple processors or cores, cache coherency becomes a major concern. This means making sure that all caches have the most up-to-date data so different parts of the system don't end up working with outdated information. Special protocols are used to keep everything in sync. The MESI protocol is a common way to maintain cache coherency in multi-core systems. It stands for modified, exclusive, shared, and invalid, the four possible states for any cache line. By tracking these states, the system can ensure that all cores see the same data, preventing errors and inconsistencies. Cache memory is a critical part of modern CPUs. It allows processors to work at their full potential by providing fast access to the data and instructions they need. Without cache, even the fastest processors would be held back by slow memory access times, making high-performance computing impossible. Mobile devices like smartphones and tablets also rely on cache memory to deliver smooth performance. Because these devices have limited power and space, efficient cache design is even more important. By optimizing cache usage, manufacturers can ensure that apps open quickly and run smoothly, even on compact hardware. Gaming consoles and high-end PCs use advanced cache memory systems to keep up with demanding graphics and real-time processing. Fast cache memory helps games load quickly, reduces lag, and allows for smoother gameplay. This is one reason why gaming hardware often boasts about its cache size and speed. Servers handle massive amounts of data and need to process requests quickly. Cache memory plays a vital role in ensuring that servers can respond to users without delay. By storing frequently accessed data in cache, servers can handle more requests and deliver better performance for websites and applications. Embedded systems, like those in cars or appliances, also use cache memory to boost performance. These systems often have strict power and space limitations, so efficient cache design is crucial. By using cache wisely, embedded devices can perform complex tasks quickly without needing large amounts of memory. Cloud computing relies on cache memory to deliver fast, scalable services to users around the world. By caching data close to where it's needed, cloud providers can reduce latency and improve the user experience. This is especially important for applications that serve millions of users simultaneously. Cache memory can help reduce power consumption by minimizing the need for the processor to access slower, more power-hungry main memory. This is especially important in mobile and embedded devices where battery life is a top priority. Efficient cache design can extend device life and reduce energy costs. Cache memory can also have security implications. Attackers can sometimes exploit cache behavior to access sensitive data, a technique known as a cache side-channel attack. Designers must take these risks into account and implement safeguards to protect user data. There are many ways to improve cache performance, from increasing cache size to optimizing replacement and write policies. Advanced algorithms can predict which data will be needed next, further reducing cache misses. Ongoing research continues to push the boundaries of what cache memory can do. The future of cache memory is exciting, with new technologies like 3D stacking and non-volatile memory promising even faster and more efficient systems. As processors become more powerful, cache memory will continue to evolve to keep up with the demands of modern computing. Artificial intelligence applications require massive amounts of data to be processed quickly. Cache memory helps AI systems keep up with these demands by providing fast access to critical data and instructions. As AI continues to grow, efficient cache design will become even more important. Big data analytics relies on processing huge datasets in real time. Cache memory allows these systems to analyze data quickly, delivering insights faster than ever before. By optimizing cache usage, big data platforms can handle more information and provide better results. Networking equipment like routers and switches use cache memory to speed up data transmission and reduce latency. By storing routing tables and frequently accessed information in cache, these devices can handle more traffic and deliver faster connections. Modern storage devices such as SSDs and hard drives use cache memory to buffer data and speed up read and write operations. This helps reduce wait times and improves the overall performance of your computer, especially when working with large files. Web browsers use cache memory to store website data locally, allowing pages to load faster the next time you visit. This not only improves your browsing experience but also reduces the amount of data that needs to be downloaded from the internet. Sum up, cache memory is a small but incredibly powerful part of modern computers. By storing the most important data close to the processor, it helps your system run faster and more efficiently. Whether in desktops, servers, or mobile devices, cache memory is essential for delivering the speed and performance we expect today. Thanks for joining us on this journey through cache memory. Understanding it is key to appreciating how computers work behind the scenes.